Greetings, pre-calc students. This is Mrs. D, here to explain how to solve rational equations. This is a nice little change of pace from all the graphing that we've been doing. We will solve equations in this format where you notice a polynomial function divided by another polynomial function. That is a rational equation. It will not always be set equal to a constant. It may be set equal to another rational function, but nonetheless you could rearrange the equation so that it was equal to a constant, like 0 or 2 or 1 or whatever. Here's our first example. We will be solving this equation by achieving a common denominator. This is a method that we used in Chapter P. We noticed what our common denominator was, but that was a little easier to do with numbers. Recall with numbers that we could not take something like 3/4 and turn it into eighths by adding 4. That is not a way to achieve a common denominator. That gives us a very, very, very different number. However, if we did want to achieve that denominator of eighths, we could take 3/4 and multiply numerator and denominator by 2. This is an equivalent value. It did not change the fraction. Only in appearance, it now has a different denominator. So with the algebraic denominators, these expressions, x minus 1 and x, you may be tempted to just subtract 1 from that denominator, but bear in mind that that does not work for numbers. Therefore, it does not work for variables because that is what they represent, numbers. When in doubt, though, let's say you had 1/17 and 4/23. If you wanted a common denominator between those two numeric fractions, you'd probably just multiply those denominators, and that may not be the least common denominator, but it would be a common denominator nonetheless. Here we'll do the same thing. So our common denominator will be x squared minus x. That was achieved by multiplying x times x minus 1. And when you write it that way, it's a little bit obvious that that's what you're going to do as you manipulate these two fractions. I will multiply this fraction, numerator and denominator, by x. In other words, I've multiplied it by 1. Now it will be 12x over the common denominator. And likewise, this 8 needs to be multiplied to get this common denominator. I need x multiplied by x minus 1. And that will also be done to my numerator, leaving me with 8x minus 8 over the common denominator. Now it is equal to the constant 2. We'll worry about that in a second. For now, let's think about why we just did what we did. We got a common denominator, so we could hopefully combine these fractions, giving us 4x plus 8. Subtracting a negative is adding over the common denominator. And yes, now we're equal to 2. This is a good time to multiply to undo the denominator. Notice that when I multiply on both sides of the equation, I'm not multiplying by x squared minus x over x squared minus x, but just that denominator value. Whatever I've been dividing by, I am now multiplying by to undo that division, leaving me with a nice quadratic equation. When you see here 4x plus 8 equals 2x squared, I will distribute minus 2x. And here we'll get some review practice from Algebra 2. I'm going to come up here for some more room. I'm setting this equation equal to 0 because factors of 0 are much more predictable than factors of any other number in our whole system. So this quadratic, whether I want to factor it or even if you want to use the quadratic formula, 0 is the number that you would like to have it set equal to. That is the setup that we must use. So when I isolate all terms to one side of the equation, I will have 2x squared minus 6x minus 8, which is equal to 0. I'm a fan of factoring, you know, so I'm going to factor out 2 just to make my job a little easier, but I'm not done factoring. I will now factor x minus 4 and x plus 1. And now I have two answers kind of staring at me, one from each factor here. If either one of these factors were 0 and I were to multiply, the end result would be 0. So I'm thinking x equals 4 or x equals negative 1. Now, in these rational equations, we've done a significant amount of algebraic manipulation of this equation. The original equation is what you need to think of lastly. So I'm going to go back to the very original, and maybe you could think about this at the beginning. I'll take that back. Think about it right away, guys. There are domain restrictions to these rational equations. The solutions that I just found are solutions to the quadratic equation that I manipulated from this original equation. But here I will notice that x cannot be 0 for the rational function to the left side of the equation, nor can x be 1. And so when I look at my proposed solutions, I just need to be sure that neither one of those values is written in my solutions, because then it would be not a solution. However, you can always check by plugging these values in or substituting and realize, oh, hey, 12 over 3 minus 8 over 4 does in fact equal 2, because 4 minus 2 equals 2. Likewise, 12 divided by a negative 2 minus 8 divided by a negative 1 would also give us 2, because negative 6 plus 8 is 2. Check, check, we have the right solutions. The other way of solving a rational equation is by clearing the denominator. Here again, we will use the common denominator, but rather than achieving the common denominator for each part of the equation, I'm going to use it as a scalar multiplier. Watch how this works. So I need to multiply both sides of the equation by x squared minus x. I am scaling this up or amplifying both sides of this equation. The right-hand side wasn't even a fraction to begin with, but what you should notice when you do this properly is that the fractions will clear out on the other side of the equation. Let us remember that this is x times x minus 1. And so when I multiply that, the factor of x minus 1 in this fraction will go away, leaving me with x times 12 minus, here when I multiply by that common denominator, the x will cancel out from that common factor, and I'm just kind of writing in free space there, but realize this x factor is what I'm undoing there, and that leaves me with 8 times x minus 1. Voila, the fractions have disintegrated. I have 12x minus 8x plus 8 remaining, equal to 2x squared minus 2x, and the rest of this algebra will continue as it did with our first example, because this is the same problem. Two answers will be found, that x equals 4 and x equals negative 1. Here's our example where I send you a word of caution. So I'm cautioning you to watch for extraneous solutions. They are solutions that are not solutions to the equation. And we think they are solutions oftentimes because the algebra leads us to those values, but again, we are significantly manipulating our equation to even get to those solutions. So be mindful. Let's go to the very beginning on this problem. We're going to remind ourselves that there are two values of x that x cannot be here. Domain restrictions, if you will. X cannot be 4 and x cannot be 2. That's valid for this function on the left-hand side of the equation, and I'm pretty sure those are the factors of this polynomial denominator, so x cannot be 4, nor can x be 2 on that right-hand side. So let's be aware of that from the get-go. I like to achieve the common denominator, so I'm going to do that. I'm going to multiply by x minus 2. I'm going to multiply by x minus 4. And notice over here I already have the common denominator that I'm trying to achieve, so I'm not going to change that one bit. So I will have x minus 2 over the common denominator plus x squared minus 4x over the common denominator. And it is equal to what it was equal to in the first place. X squared minus 6x plus 8 is the denominator with the 2 numerator. Now this is going to work out real slick because I can combine these two fractions, and I have x squared minus 3x minus 2 all over the common denominator. And actually in our next move here, I'm going to anticipate multiplying to get rid of the dividing. And when I do that and multiply by that common denominator, you're going to see this kind of is really swift, that common denominator, which is x squared minus 6x plus 8, but I don't want to write it again, will undo on both sides of the equation, leaving us with x squared minus 3x minus 2 equal to 2. Once I set this equal to 0, as I will in most quadratic situations, I have this expression is equal to 0, I'm going to factor, and what a coincidence, I promise you. I found these problems in complete isolation. And it factors exactly the same way, but look, we have x equals 4 and x equals -1. These are the same proposed solutions to our last example, but this looks drastically different. Anyways, are both of those solutions, or is one of them extraneous? And that's what you have to be aware of. If I go back to the very beginning, notice that x cannot be 4, so that is not a solution to this equation. It's an extraneous solution. It was found through my algebraic manipulation, but if I were to look at the graph of this function even, that's not a valid value of x, it's actually a vertical asymptote. Is x equal -1 a valid solution? Sure. Neither one of those restrictions includes -1. So here we have one solution. I'm only going to list the one solution. The other solution that I found is not valid. For our last two examples, I chose some very nice looking equations. They're not so intimidating looking maybe. And maybe we're trying to throw out a different strategy here on this first one. There is a common denominator of y minus 2 if you really wanted to achieve that on both sides of the equation. But I would maybe just go right for some multiplication on this one to start off my work, rather than trying to mess around with making a bunch of fractions. Let's get rid of that denominator straight away, and we will have 2 minus y equals y squared minus 2y. So don't forget about other methods that you've used in the past. No need to force it to be a common denominator situation here. Let's just get rid of the denominator right away. I'll set it equal to 0. It's quadratic once again. And I have y squared minus y minus 2. Some of these are quite contrived. They almost always will factor. And if they don't, which I say that now and they almost always do, but there are some that don't, you'd probably have to use that quadratic formula or even a graphing method to solve the equation. Here my two possible solutions would be y equals 2 and y equals -1. As I go back to the very original problem here, I had a denominator of y minus 2, which tells me a domain restriction, which this is kind of counterintuitive to write. Y could not be 2, and look, I've tried to list it there. I have an extraneous solution. Y cannot be 2, even though my algebraic manipulation led me to it. Can it be -1? Let's see, 2 minus a -1 divided by -1 minus 2 would be 3 divided by a -3, which is -1, the value of y. Neato Frito, it works. One solution, once more. At this point in time, it might be wise to pause the video and try this last problem, this last situation where I'm asking you to solve. See if you can do it on your own, and then come back and watch me do it. And I'm back from a short commercial break. I've achieved a common denominator of a squared minus 9. Did you do the same thing? These two fractions needed to be changed or scaled by 1, a fancy form of 1. And I will move forward now with the problem by writing it in a more simple fashion. I will have 5a minus 9 equals a plus 3 over a squared minus 9. This almost seems too easy. Let's see what happens next. If I multiply now, not to change the denominator, but to get rid of the denominator, multiplying both sides by a squared minus 9, I am left with 5a minus 9 equals a plus 3. This is not quadratic, so I'm just going to isolate a to one side. This is a linear equation. One solution will be found here. 4a would equal 12. If I divide, I find that a equals 3. And I go back to the very beginning. Remember that caution on the last slide. Think about your domain restrictions. Here in this function, a could not be 3. A could not be -3. Either one of those are restricted values of a, and we happen to find one of them. So guess what? This is an extraneous solution, which means, well, if you found one solution and it's not a solution, there is no solution to this problem. There's no real value of a for these two quantities will be equal. Try as you may. You could even check it out graphically. They will never ever intersect. This function and this function have nothing in common. That's the end of our video. Hopefully you've learned how to solve a rational equation. Don't forget to check for extraneous solutions. Mrs. D signing out.